Number 1. A group of 11th graders wanted to estimate the proportion of all students at their high school who suffer from allergies. Each student in one group of 11th graders took a random sample of 20 students, while each student in another group of 11th graders each took a random sample of 40. Below are the two sampling distributions shown as histograms of the sample proportion of high school students who said that they suffer from allergies. Which histogram is based on random samples of size 40? Explain your reasoning. So, this lesson was all about sampling distributions. And a sampling distribution is when you take a sample, find, in this case, the sample proportion, and then we plot that sample proportion. And we keep on doing this. We keep taking a sample, finding our sample proportion, and then add another dot to this, in this case, the histogram, not a dot. We're going to add it to the histogram here. So these distributions here are a whole bunch of distributions of p-hats. Each bar here, each frequency here, means that you have one sample of however many students, all of that entire sample condensed down to one p-hat. And during the lesson, we talked about the idea, the larger the sample size, the larger the sample size, the less variation in the sampling distribution. In the sampling distribution. Which means I need to figure out which of these has less variation or less spread. So, which of these two distributions is tighter together, has less spread? So, looking at both of them, this ranges from 0.3 to 0.85, whereas this other distribution on the left ranges from 0.4 to 0.8. So, I'm going to say this distribution has less spread, or less variation. Which means this is the sample size, n equals 40. The larger the sample size, the less variation in our sampling distribution. Our p-hats in this case are going to be closer towards that center. So this is going to be n equals 20. So based on the sampling distribution for sample size of 40, so we're looking at the left histogram here, which is the best estimate for the true proportion of students who have allergies? Now, they didn't ask everyone who had allergies, they only asked a sample of them. So we don't really know the true number because we didn't do a census. We didn't ask everyone in the building. They only asked that random sample, and these were the p-hats of their random sample. So, what's the center of this distribution? The center of this distribution, I would say, is about here. That's the balancing point. So I would say the center is 0.6. So what's my best guess of that true population parameter? Our best guess for P, the population proportion, or population parameter, the true proportion is 0.6 because it's the center of our sampling distribution. So there's that thing called the central limit theorem that we talked about in class that said the bigger your sample size, the less variation, and our sampling distribution is going to be centered about that true population mean. The center of the sampling distribution is going to be close to the true population parameter that we don't know. Number 2, the nurse in your school district would like to study the proportion of all high school students in the school district who usually get at least 8 hours of sleep on school nights. Suppose each student in your class takes a random sample of 20 high school students in the district and each calculates their sample proportion of students who said that they usually get at least 8 hours of sleep on school nights. Below is a histogram of the sampling distribution. So this histogram is, because it's a sampling distribution, is a bunch of p-hats. People took a sample, found the proportion of students who said they slept more than 8 hours a night on school nights, and plotted that one p-hat in this distribution. So each part of this distribution, each frequency on this distribution represents a sample, and we found the p-hat of that sample. Do you think that the proportion of all high school students who usually get at least 8 hours of sleep on school nights could have been 0.4? Could our true population parameter be 0.4? Well, if I go to my sampling distribution, 0.4 is here. Would we consider that an unusual value? No, we wouldn't consider it unusual because it's towards the center of the distribution. It could be 0.4. 40%, that would mean that our true proportion would be 40% of students get at least 8 hours of sleep on school nights because it's towards the center of the distribution, the sampling distribution. I'm going to put that word there, sampling distribution. That's important. Could it have been 0.55? Could it have been 55%? So 55% is getting a little bit more unusual, but it's still towards that center. It's still in that middle chunk of the distribution. It's not that unusual. 0.55 is also possible. For the same reason, it's not that uncommon. It did happen. It's towards the center of the distribution. Could it have been 0.75? Could it have been 0.75? 0.75 is all the way over here. No, I'm going to say no. It could not have been 0.75. Because none of our samples had a p-hat of, how high did it go? The highest it went was 0.7 or greater. The highest possible p-hat we could have gotten was 0.7. So there's no way the true population proportion was 0.75 based on that distribution. Suppose students had taken a random sample of size 60. How would the distribution of sample proportions be based on the sample size of 60 differ from size 20? So as we increase sample size, the standard deviation of our sampling distributions, the variation decreases. So this lesson was all about introducing us to sampling distributions, where we take a sample, find a p-hat, or later we're going to find a mean. We're going to find a sample proportion or a sample mean, and we're going to plot that one point. Then we're going to go out and take another sample, find another sample proportion or sample mean, and plot that point. And we're looking at a distribution of a bunch of samples. We're looking at a distribution of sample proportions, or later we're going to look at a distribution of sample means. And we're going to use this sampling distribution to make inferences about that true population parameter that we don't know, the true population proportion or the true population mean. That's what we want to know about, and our sampling distribution is going to help us out make inferences about that from the data we collect.